So next here, we're going to calculate the lattice energies using the Born Haber cycle, as I wrote here. And as I promised in the last video, I'm a man of my word. All right. So like I said before, it's essentially using Hess's law to do this process, and it's to figure out delta H reaction for a series of reactions that are ultimately going to take us from our elements to our ionic solid. So we have our pure elements, they're going to form an ionic solid, but we're going to take a little pit stop in the middle. We're going to turn them into gas phase ions. So we're going to have our elements, we're going to turn them into gas phase ions, and then boom, they become a solid together at the end. And we just do it step by step in these calculations. And as my example, surprise, surprise, we're going to talk about the formation of sodium chloride. And your book ripped me off, all right? I did this example and I realized your book does the exact same one. I normally try to do something supplementary to the book, but I can't help it if they steal my #1 compound, all right? That's not on me. But, you know, if we know our delta H of formation for our compound, then we can go through this process and we can find the lattice energy. And so for sodium chloride, we got 1 mole of sodium plus a ½ mole of Cl2 gas. This is going to give us 1 mole of sodium chloride. And it just so happens, the luck would have it, we know delta H naught of F. We know our formation, our enthalpy of formation, to be negative 411.2 kilojoules. All right. So 1 mole of sodium chloride, to make that, we will release 411.2 kilojoules of energy. All right, so we're going to go off of that. And so we're going to do this kind of in 2 steps, just like I have it diagrammed here. We're going to go elements to gas phase ions. That's the first thing we're going to do. And then we're going to take those gas phase ions and we're going to make an ionic solid out of them. And so this first piece is the tricky one. All right. And so we got to go sodium to sodium gas to the sodium plus ion. So this is going to involve looking up a lot of things in tables, potentially. So when we go solid to gas, that's sublimation. It's a phase change. Phase changes have a delta H associated with them. And some poor fool had to measure the energy of sublimation, or the enthalpy of sublimation, for sodium at some point. That's fun. You don't have to do that yourselves. You just go with, oh, the table says 109 kilojoules per mole. Good enough for me. So we look that up. So we know to get to this step, 109 kilojoules per mole. Okay. Then we've got to ionize it. Well, we're going to take an electron away. We look up our ionization energy. To lose an electron takes energy. You know, sodium doesn't hang on to it super strong, but there still is an attraction there to pull it away. And so we look at that and we go, okay, well, the ionization energy, the energy required to remove the outermost electron from sodium, 495 kilojoules per mole. So we've got all our numbers, we've got all our pieces. And again, these are from tables. Hopefully smart work is nice, gives you the numbers with the problem, or at least tells you what page to look stuff up on the table. But ultimately, these are measured values that are predetermined. You're not necessarily going to be calculating them. We'll get into a little more detail on some tricks you can do with these problems in a little bit. But we're just using this to find the lattice energy right now. All right, so that gets us to our sodium plus. So we're halfway there. We've got 1 ion down, 1 to go. Here's the good news. Chlorine, it's already a gas. We don't have to do a phase change. No sublimation, no evaporation, nothing like that. It's a gas. Okay, but it has a bond. I don't want Cl2s, I want Cl, so I've got to break this sucker in half. And so half of Cl2s become just Cls by themselves in the gas phase. So a single chlorine atom. And so this isn't, you know, necessarily favorable. Again, this is sort of a theoretical workup. You're not necessarily going to see Cl atoms floating around by themselves. And to do that, we have to look up the bond energy. So there's an enthalpy associated with the bond. And we got to multiply it by half because we're only dealing with half a mole here. And so half of a mole is going to come out to be 120 kilojoules, you know, per half mole. All right. So that gets us to the, you know, single atom gas phase. We still got to ionize it, so we have to put on 1 electron. And so we have to look up the electron affinity. How much attraction does chlorine have to 1 more electron? And it turns out it's negative 349 kilojoules per mole. So we only have to put 1 electron on, so there's only EA1. We don't have to worry about electron affinity 1. Now, if you're ever working on a problem and you have to ionize it multiple times, well, you know, maybe you have like magnesium or something like that. And you get magnesium in the gas phase, you get magnesium plus, and then you got to get it to magnesium plus 2. So you have to use ionization energy 1 and ionization energy 2. So for every electron you're taking off of your cation, you have to use every corresponding ionization energy in a row. You don't just get to skip them, you got to use them all. And if you have anion that's taking on multiple electrons, you have to use all of their electron affinities. So you get electron affinity 1 for the first electron, electron affinity 2 to add the second, 3 for the third, so on and so forth. So be aware of that. Like this, there could be more steps in these. This is a somewhat simple ionic compound. They can get a little more complicated. So we look up all our values. That gets us gas phase sodium, gas phase chloride. And the next step, they just come together. Our gas ions become solid ionic compounds. They stack together in what we call a lattice structure. And that's what we call this lattice energy. It's the energy associated with forming that lattice structure. And so there's a delta H associated with this. This one we don't know. This is what we have to figure out. Now, if we back up a little bit and we look at our whole equation here, delta H of formation is equal to all this stuff added together. That's where the Hess's law part comes in. And I'm going to clear the board in a little bit and talk about that and make sure that point is clear. But what we're doing is we're taking this whole process, we're breaking it into pieces, and those pieces have to add up to the whole. And so when I add this and this and this and this and this, I'm going to get negative 411.2 kilojoules. And I know everything but the lattice energy. And so to write that out in math, my enthalpy of formation is equal to the sublimation of sodium plus its first ionization energy plus 1/2 the bond energy of chlorine plus the electron affinity, first electron affinity of chlorine, and the lattice energy. Now this is what we don't know, right? That's what we don't know. We know every other piece in this, and that's key. And that's what can change with these problems, by the way, is maybe you don't know this, or this, or this, or that. Essentially, there's some number of variables, and again, the old tried and true test of, I gotta tell you all but one of the variables is gonna hold. So right now we don't know the lattice energy, but maybe you do in another problem, but you don't know an ionization energy or whatever. You just work it up to find whatever you don't know. So we don't know what U is. We solve for U through the cunning art of subtraction. We subtract everything else from the right-hand side. We get U by itself. All this moves to the left, and I flipped it because, you know, I like my equal sign there. And so now we have our enthalpy of formation, and we just subtract all the other pieces from it. We bring the numbers into it. I was kind of running out of board space, so I didn't do that. But if you total it all up, it'll be negative 786 kilojoules per mole. So that is our lattice energy. And that's how we find it with this process. And so I'm going to clear the board here, and I'll show you why I keep saying this is like Hess's law. So just hold on 1 minute. So what we have here is just the same process. We're still talking about making sodium chloride, but I've just written it a little differently. And so if we stack all of those chemical processes that we did, you know, we go from sodium solid to sodium gas, we have a delta H associated with that. Well, that was the sublimation, but we'll just call it delta H1. We're not going to do this numerically. This is just to show how this is Hess's law. And so if you remember, if there's anything on the left and the right that show up the same, anywhere down the line, we can cancel them out. And so sodium gas, sodium gas, sodium plus gas, sodium plus gas, a half of Cl2 doesn't seem to cancel, but Cl gas by itself does. Cl minus cancels with Cl minus. And so let's see, there's nothing to cancel solid sodium, there's nothing to cancel chlorine Cl2 gas, there's nothing to cancel NaCl solid, and so we get an overall equation of Na solid sodium plus a half mole of Cl2 gas gets us NaCl solid. And so that was our equation for our formation process. And so there's a total, we add all these up, we get a total delta H. Well, that's equal to our delta H of formation, because this is a formation equation here. We're putting together two different elemental substances to make something else. So that's the formation of sodium chloride. And so this is, everything I did before was just a fancy way of dressing up Hess's law. It's just a very specific situation, making ionic compounds. All right. So another way to look at this is an energy diagram, or an enthalpy diagram, excuse me. I don't know why all these thermodynamic terms got to start with E, but That happened long before I was alive, so it's not my fault. You blame someone else for it. But if we look at this enthalpy diagram, so we go low to high. So we start out and we've got our elemental compounds. We sublimate our sodium, so we go from solid to gas. Now we have sodium gas plus half of a mole of chlorine gas, Cl2. Then we're going to ionize the sodium, so now it's Na+. Then we're going to break apart the chlorine molecules to make just single chlorine atoms. And then we're going to come over here and we're going to ionize. And that's going to, so everything we did here, we had to put energy in. When we ionize the chlorine in the chloride, we add an electron to it. It is actually lower energy. It releases energy. And then the gas ions come together and a bunch of energy is released to make sodium chloride. Solid sodium chloride, excuse me. And if we look at this, if I make a little dash line here, if we go from our starting point to just our end point, that's our delta H of formation. And so overall we had a negative value. This isn't necessarily drawn to scale, but the general up and down portion is correct. And so both of these lines here correspond to Na plus Cl gas, so then we make the anion, and then we put the ions together and make a solid, and that's going to release a bunch of energy. So making the ions initially in the gas phase, yeah, we got to put some work into it, and then we start getting stuff out at the end. And then boom, we have a solid. So there's a reason you don't see sodium chloride just poof, a cloud of it disappear out of your salt container. It's going to stay solid. And it's really, I mean, it's really going to stay solid. You're not going to really be able to melt it with any device in your house. If you've ever seen footage of lava, you've seen liquid ionic compounds. That's how hot they are. So, and I haven't really seen them in the gas phase very much. And hopefully I never do in person, right? So that's kind of the whole idea. And again, just to kind of back up and look at this side again, what I was talking about earlier is we've got a series of delta H's for all of these different equations. You have to be able to determine what they all are some way or another, except for one, and it could be any one of these ultimately in these questions. And so if you can set this up like I did before, you figure out the missing piece, you solve, and so this is also equal to, you know, delta H1 plus 2 plus 3 plus 4 plus 5, and you just solve for the one you don't know. All right, and so this is very mathematically intensive, but if you're comfortable with Hess's law from 221, or even just vaguely remember it, you've done the work, and so then it's just a matter of IDing what constants do I need to look up to solve this problem. And so you want to diagram when you work on these problems. That's my advice. Don't just try to solve it. So understand what we're going to do. We got to get here. And whatever you do to do that, break bonds, ionize once, twice, 3 times, whatever it takes to get there. And then, you know, whatever U is. Maybe we tell you, maybe we don't. If we don't tell you, guess what you're solving for? If we do, it means you're solving for something else. All right. So we got one more little video on this section, and then it'll be on to the next one.